Hello and welcome back to the Deep Learning course. This week we'll talk about a simple type of neural networks, so-called multi-layer perceptrons, or in short, MLPs. We'll see the close relationship between these MLPs and logistic regression, and in particular that MLPs are an extension of logistic regression that uses nonlinear learned basis functions. We'll also look into the representational power of MLPs. In this first video of the week, we will recap logistic regression. I expect that you've seen this before in a standard machine learning class, but it's nevertheless useful to do this here quickly in order to remind ourselves and in order to establish some notation that we'll be using afterwards. We'll also have a look at the cross-entropy loss that's used within logistic regression, and that is also the most common loss used in deep learning. Let's dive right in. Recap of logistic regression. The first thing to remember about logistic regression is that despite its name, it's not a regression method. It's a classification method, and the decision boundary is a linear function. So we'll have some class 0 here and a class 1 here, and the decision boundary between the two is a linear function. And this linear function can be described by a linear equation like this here. And this particular linear function here can be described by this weight vector. Now, what logistic regression does to classify new data points x is to multiply them with this weight vector and to check if the result is greater or equal 0. If yes, it predicts a point in class 1, and otherwise it predicts it in class 0. Also notice that we use this vector notation here. And in order to do that, we have to actually use an x0 equals to 1 for bias. Here we only have x1 and x2, and in order to actually get this bias term, this w0 times, this is basically times an x0, and the x0 is set to 1. All right, and that allows this nice vector valued notation here. Now, let me also remark that even though in logistic regression the decision boundary is a linear function, this is only linear in the weights. It's not necessarily linear in x. So if you use basis function regression, you could just as well write wt phi of x. So you could do wt phi of x, where phi is some nonlinear function. And then logistic regression will give you a nonlinear function in x. But it's still going to be linear in the weights w. And this is precisely what we'll do in the last layer of our neural networks later on. We'll have a nonlinear function phi of x, namely the whole neural network that takes the input x and comes up with the inputs to the final layer. And in the last layer, we'll just have a logistic regression based on these inputs phi. Another thing to remember about logistic regression is that it yields a probabilistic estimate. So how likely it is actually that a data point x belongs to class 1 and how likely it is that it belongs to class 0. It does this by directly computing this probability as h sub wx equals, well, this linear function wtx fed through a nonlinearity, and this nonlinearity is a logistic function g, where g of z is defined as 1 divided by 1 plus e to the minus z. And this logistic function is depicted here. So if you have a large negative input, this function becomes 0. And if you have a large positive input, then this function becomes 1. So this is a so-called squashing function. It takes an arbitrary range and squashes it to the interval 0 to 1. So notice that we are maximally uncertain about points on the decision boundary. We said that the decision boundary is where wtx is 0. So that would imply here that, well, wtx is 0. So our logistic function is going to be 0.5, and we're maximally uncertain. Whereas, for example, if our WTX is 5, we're already quite certain with a probabilistic estimate of 0.993, and that this is a positive class. The loss function typically being used in logistic regression is called cross-entropy loss. And we'll actually look at this in detail now, since this is the same loss function that we typically use in deep learning. And we'll actually derive this from first principles now for the case of logistic regression, but it's going to be the same for deep learning later on because we just going to have a logistic regression in the output layer of our neural network. So the way we're going to derive this is by looking at the class for a new data point x. And the true value of this class, little y, that is unknown. And so we therefore model it as a random variable. And since random variables are typically denoted with capital letters, we denote this here as capital Y. And this particular random variable, capital Y, has a so-called Bernoulli distribution because there's a domain for this true value of little y of 0 or 1, and the Bernoulli distribution is just the standard probability distribution over a Boolean domain, and it's parameterized by one parameter p that says how likely the outcome is to be true. And it is this parameter p that we predict with logistic regression. So the output of logistic regression is directly going to be this probability that is going to be the estimate of the model that this Bernoulli variable is 1, given our input x and our weight w. Now notice that the actual true labels, little y, they're still discrete, either 0 or 1. So if we have a formula here for predicting y equal 1, then well, we know that the estimated probabilities for y equals 1 and y equals 0 have to add to 1. So we directly also have a formula for our prediction that y equals 0. And namely, it's just 1 minus p model of y is 1 is just 1 minus our typical output of logistic regression. And with this, we can now write down the likelihood of the true data under our model's predictive distribution. So our model predicts class y equals 1 with this probability here, predicts class 0 with 1 minus that probability. And so if the true class is actually 1, well then our likelihood is going to be exactly this output of logistic regression. And if our true class is 0, then our likelihood is going to be 1 minus that output. And now that we have this formula for the likelihood of the true data under the model, well, we actually just want to maximize this by actually changing the w's. In machine learning, however, we don't typically maximize an objective function, but we rather minimize a loss function. And so that actually then gives rise to the cross-entropy loss. It's really very much like this likelihood here, but instead of having just exactly this likelihood, we take the logarithm and put a minus in front. So we put the minus in front in order to minimize our loss function rather than maximize the probability. And we take the logarithm actually in order to avoid multiplying a lot of probabilities. In machine learning, we typically sum log probabilities. So a typical loss function is actually the negative log likelihood of the true data under the model. And in this case here, well, that is actually just exactly minus the log of this here. So that is our cross-entropy loss function. And we're going to use exactly the same cross-entropy loss function in order to optimize our deep learning models. Here's a quick visualization of this cross-entropy loss function. So up here, I just copied this equation from the previous slide. And there are two cases in this equation. The first case is where the true value of y is 1. And in that case, the loss function is minus log of hw of x. This is 0 if hw of x is 1, because then we have minus log of 1, which is 0. And it's good that the loss is 0 in that case, because then the model is correctly predicting the class to be 1 with high confidence. On the other hand, the loss is going to go towards infinity if hw of x is going towards 0. And again, that is good because in that case, the model is falsely predicting the class to be 0 with high probability. So if we're mispredicting with high confidence, that is penalized a lot. So likewise for this second case, where the true y is 0, our loss function is going to be basically the mirror image of what we just saw. So if hwx is 0, then the loss is 0 in this case, because well, the true class is 0. And if the prediction is close to 1, then the cross-entropy loss goes to infinity. So the takeaway message from this is that predicting the wrong class with very high confidence for a data point is penalized very heavily, much more heavily so than being uncertain about even 2 or 3 data points. So being uncertain would be here. That is actually not penalized all that much compared to being really certain about a point being 0. That is actually truly 1. Now, I would also like to mention that cross-entropy can be written in a different way than we have done so far, and is in fact often written differently in deep learning. So up here, we have the form that we've used so far, and we can now realize that the true label y is either 0 or 1 in order to rewrite this in a single line. And we can simply verify that this single line matches the formula up there by a case-by-case analysis. So let's say y equals 0. In that case, this first term here goes away because it's 0 times another term, and 1 minus 0 becomes 1. And all that remains is this term, which is actually identical to the term up there. And then let's go to the second case. And let's say y equals 1. Y equals 1, then we have this term here remains. And here we have 1 minus 1 is 0, so this whole term goes away. And we have exactly the same term remaining here as up there. So we verified that the single line matches the case-by-case analysis up there. And this is, of course, very convenient. If we can write the cross-entropy in a single line, we can write formulas much nicer, etc. And we can also use shorthand notation to say, well, this is the output of logistic regression. That's our probabilistic prediction, and we typically label this y hat. And then we can write the cross-entropy in a very nice short form like this, with the predictions y hat and the true label y. And well, it doesn't look like this anymore, but this is still the negative log likelihood of the true label under the model. So far in this video, we just looked at the cross-entropy loss for a single data point, and I've copied the loss function from the previous slide over here. But of course, in practice, we need to compute the loss function for our entire training data set. And there's no magic there. We just sum over the individual negative log likelihoods. And well, now we have sub-indices y sub n and y hat sub n, and nothing else really changed. So we're summing up these losses here because we're already working in the log likelihood space. So if we had likelihoods, then we would multiply them together, but log likelihoods we add together. And so this overall loss, L of W, is simply a function of w, and actually it happens to be a convex function for the case of logistic regression. And that's why this cross-entropy loss is a very popular loss function in combination together with logistic regression, and we typically minimize this function by some iterative optimization algorithm such as stochastic gradient descent. And in deep learning, we're going to have very similar functions, except that in that case, they're going to be non-convex, but we're still going to be using very similar methods, in particular also variants of stochastic gradient descent. Okay, that brings us to the end of this video. And as always, I'd like to leave you with some questions to think about for yourself. So thank you, and I'll see you in the next video.